Today we want to talk about one example of solving a differential equation, in this case a second order linear constant coefficient non-homogeneous differential equation, where the function on the right, the non-homogeneous part for the differential equation, is one which involves step function. We want to solve the initial value problem y double prime plus y equals g of t, with y of 0 equals 0 and y prime of 0 equals 1, where g is the function whose graph is below. This is a step function. We see g is 1. We can write that out here. G of t is 1 if t is between 0 and 1. It's negative 1 if t is from 1 to 2. And it's 0 if t is greater than or equal to 2. So imagine the graph of g just continues as 0 beyond that. And of course, this is t here. So what would this differential equation model? Well, this is actually, examples like this are discussed in section 6.4 in the book. This is about modeling, say, a vibrating system, a mass spring system, where there's an external force applied, and that external force is modeled by g of t. So for the first 1 unit of time, say for the first 1 second, it's just a constant force of 1 unit to the right. And then all of a sudden it switches to a force of 1 unit to the left for 1 second, and then the external force turns off. So imagine this problem, you can imagine in the following way. Here we have a mass spring system. Here's our y-coordinate, say here's 0. It starts y of 0 equals 0, so it starts at the equilibrium position, but y prime of 0 equals 1, so it starts moving to the right with velocity 1. And initially, for that first 1 second, there's an extra external force to the right of 1 unit. Then after 1 second, that changes and it gets pushed back to the left with an external force. And of course, the spring is always pulling it to the left as well. What will happen to this? The question is, what will happen to this system, both in the short term and long term? Can we find an exact solution here? And the answer is yes, we can use the Laplace transform, because we know how to take the Laplace transform of a step function like this. The first thing to do is model the step function. Let me actually do that over here. How would we model the step function? Write it in terms of standard step functions. Well, here's one way to define g, but a more useful way for us will be to write it as the constant 1, which would be always 1 like this. But then, starting when t equals 1, it drops by 2 units. So I'm going to subtract 2 u sub 1 of t. That means that between 0 and 1, it will be this constant 1. But beginning at 1, we drop it 2 units, so we're down here, and it would be at negative 1 forever if I just left it alone. But then what happens beginning at 2? Well, then it increases by 1 unit again, so I have to add u2 of t. So even though I wrote that kind of sloppily there, g can be written exactly as 1 minus 2 u sub 1 of t plus u sub 2 of t. Remember, our standard step function u sub c of t is defined as 0 if t is between 0 and c, and this 1 if t is greater than or equal to c. So it's 0 until you get to c, and then it's 1 after that. So here we have the same problem where I've written g in terms of these standard step functions. And we want to take the Laplace transform of both sides in order to solve this differential equation with the initial value here. When we take the Laplace transform of y double prime, we get s squared times capital Y. Here, capital Y will be the Laplace transform of little y. So we get s squared times y minus s times y of 0 minus y prime of 0. So just putting in the initial values, we have minus s times 0 minus 1, plus the Laplace transform of little y, which is capital Y here, and that has to equal the Laplace transform of g of t. Well, how do we take the Laplace transform of G? Using the linearity, we just take the Laplace transform of each piece. The Laplace transform of 1 is just 1 over S. The Laplace transform, remember we talked about this in the previous video lecture, the Laplace transform of u sub c of t is precisely e to the minus cs over s, so that the Laplace transform of u sub 1 of t is e to the minus s over s, and we have minus 2 of those, and then we add the Laplace transform of u sub 2 of t, which is e to the minus 2s over s. We then just take this equation, we solve for capital Y, which is L of little y. That should be these type of brackets here. And we get here, when we gather the capital Y terms, we have s squared plus 1 times capital Y. We move this 1 over to the right side, and then we divide by s squared plus 1, and we get this slightly messy thing. Now, the only way we're going to deal with this is to apply partial fractions on the right here. This first term here is already in its partial fractions final form, and you should recognize that as just the Laplace transform of the sine function. So that's really fine as it is. But here we have this numerator, 1 minus 2 e to the minus s plus e to the minus 2s, times this function, 1 over s times s squared plus 1. And you can write down the partial fractions decomposition of this, which would just be a constant over s plus a constant times s plus a constant over s squared plus 1. When you solve for those constants, you'll see very quickly this is just 1 over s minus s over s squared plus 1. You can pause the video here and just try to work out that partial fractions decomposition for yourself, and you'll see that that works out. So what do we get? Well, we get the 1 over s squared plus 1 that we had before, and then we have this numerator here times this quantity on the right, which is that numerator times 1 over s minus that same numerator times s over s squared plus 1. So, does that tell us how we can solve the initial value problem? Well, I've rewritten what we had before. Capital Y, which is the Laplace transform of little y, is this exact same quantity that we had written down before. So now we just want to take the inverse Laplace transform of each and every piece. And at this point, I'm hoping you can recognize the inverse Laplace transforms. It'll take some practice for you to be able to do so. The inverse Laplace transform of 1 over s squared plus 1 is just sine of t. The inverse Laplace transform of 1 over s, just that first piece here, the 1 over s, is just 1, because Laplace transform 1 is 1 over s. The inverse Laplace transform of minus 2 e to the minus s over s is just minus 2 u sub 1 of t, since the Laplace transform of u sub 1, we've already seen, is e to the minus s over s. The inverse Laplace transform of e to the minus 2s over s is u sub 2 of t. So we've found the Laplace transform of this entire second term here with the 1 minus 2 u sub 1 of t plus u sub 2 of t. That's exactly that function g of t that we were talking about. Now we have to find the inverse Laplace transform of that same numerator times s over s squared plus 1. Well, how do we find the inverse Laplace transform of 1 over s squared, let me say that again, inverse Laplace transform of 1 over 1 times s over s squared plus 1. That's just cosine t, and there's a minus sign that comes from there. What about 2 e to the minus s times s over s squared plus 1? Well, remember, if you want the inverse Laplace transform of e to the minus cs times some function f of s, that will just be exactly u sub c of t times f of t minus c, where this should be t minus c. Let me fix that. Where here the Laplace transform of little f is just capital F. In other words, the inverse Laplace transform of capital F is little f, but because it's multiplied by e to the minus cs there, you have to multiply little f by u sub c of t and shift the variable by c inside. So that might be a bit tricky, but that's a very important thing here. So how do we find the inverse Laplace transform of e to the minus s times s over s squared plus 1. That's like a cosine function, and of course, like minus minus gives you a plus, and 2 times a cosine function, but we have to multiply by u sub 1 because it's e to the minus s, and replace t by t minus 1. So we have 2 u sub 1 of t times cosine of t minus 1. Similarly, we have a minus e to the minus 2s times s over s squared plus 1. The inverse Laplace transform will again be a cosine function, but now it's multiplied by u sub 2. The minus sign comes from there. And it's not just cosine of t, but because of that e to the minus 2s, it gets shifted to t minus 2. So that seems like a big mess, but let me show you how you can understand that. I'm going to rewrite these terms. Here's the stuff without any of the u functions. We have 1 plus sine t minus cosine t. The graph of that function is exactly this black piece here. Because when t is between 0 and 1, all of the u1 and the u2s are 0. So y is just 1 plus sine t minus cosine t. Now, when t is between 1 and 2, the u1s will be 1, but the u2s are still 0. So what is our function y? It's all of this stuff we had before, 1 plus sine t minus cosine t, and now we add the stuff that has a u1. We have a minus 2, and we have a plus 2 cosine of t minus 1. Cosine of this quantity, t minus 1. And so when I put that all together, I get this red part here. And what happens when t is greater than or equal to 2? Well, then the u1 is 1, and the u2 is also 1. So y will be everything we had before. It will be 1 plus sine t minus cosine t minus 2. You could simplify that, obviously, plus 2 cosine of t minus 1. But now we add in the u2 terms, so we get a plus 1 from here, and then we have a minus cosine of t minus 2. And if we just do the most basic simplification, the 1 plus 1 and the minus 2 cancel, we end up with sine t minus cosine t plus 2 cosine of t minus 1 plus, I'm sorry, that's minus cosine of t minus 2. And that's shown here in the green. This function here, just by combining the different trig functions, can actually be written as some amplitude times a single shifted sine or cosine wave here in the green. Now, it might look like the whole thing is like that, but this beginning part is distinctly not exactly a sine wave because it's the 1 plus sine t minus cosine t. It's very different. And even this red part is very different as well. You'll notice that at the boundary, things look very smooth, and they have to be, because in order to be a solution to this differential equation, we need our solution y to be continuous, of course, and differentiable. So you'll notice that where we shift from one of these functions to another, you'll see that the thing we're adding takes the value 0 right at that place where we're shifting, so there's no jump discontinuity here. Our solution function is continuous, and if you check carefully, you'll see it is actually differentiable, even here at these boundary points where we're shifting here at 1 and 2. So the Laplace transform gives us a good way of being able to handle functions g of t, which in this particular type of example is our external force function, functions which are discontinuous. They have jump discontinuities. Is there any other way we could handle a problem like this? Well, the answer is yes. Let me go back up to the earlier page. If we hadn't done anything with Laplace transforms, you could actually still solve this problem by solving this differential equation with this initial condition, but instead of with g of t, just imagine this were just the constant function 1 here. So you had y double prime plus y equals 1. And you would get the exact same solution we obtained before between t equals 0 and t equals 1. Then ask, what is the value of our solution function and its derivative, not at 0, but now at 1, and use that as your new initial condition to solve the problem y double prime plus y equals minus 1. That's what g of t is between 1 and 2. So solve this differential equation with new initial conditions, not y of 0, y of 1 equals whatever that is. I'll call that y1, and y prime of 1 equals whatever it is, y1 prime. Once you know from the first differential equation you solved what those values at t equals 1 look like, solve a new differential equation with these new initial conditions, solve y double prime plus y equals minus 1 there, and you'll see what our solution has to look like between 1 and 2. Then what do? You find out what this new solution looks like at 2, what its value and the value of its derivative is at 2, and then you solve y double prime plus y equals 0 with new initial conditions. Y of 2 equals whatever this new value is, y sub 2, and y prime of 2 is whatever this new value is, y2 prime. And you'll see what happens after that point. And when you do that, you should get exactly the same solution that we saw here. But the Laplace transform provides a really nice, elegant way of putting this all together and doing it all in one fell swoop.